All right. Now we'll talk about what we call the transient behavior of L over R circuits, which means the in-between times. So not just the short time when an inductor behaves like a gap, or the long time when an inductor behaves like a short circuit, but we'll also look at the in-betweens. So here's where we'll pull out the differential equations, the time constants, all of those things we did with RC circuits. We have equivalent formulations for in an LR circuit. So we've been calling them L over R circuits because the time constant isn't LR like it's RC for a capacitive circuit, but it's L over R. And first we should look at this and make sense that the time required for an inductor to reach a certain percent of its steady state current depends proportionally on inductance and inversely proportional to resistance. So first, if the inductance is higher, we'd expect a bigger time constant because there's more inertia. So the inductor is going to resist change more. But if the resistance is higher, we would get a lower current. So we'd get a lower current rate of change. So the inductor would have less opposition to the current that way. So that's why we have one of these factors increasing tau and one of them decreasing tau. And again, the interpretation of the time constant, it's sort of this idea of a half-life, except it's more of like a 63% done life, where after one time constant, the current has reached 63% of either its maximum value, if it's increasing, or it's decreased by 63% if the current is lowering over time. So here's our visualization of one time constant. So this would represent an inductor that initially has no current through it, and then it's initially fighting that current change. But as the circuit responds with less and less current change, we see it approaches a steady state value, as we looked at previously. So just for a quick ranking task, we have 3 circuits. All the inductors are identical. All the resistances are identical. And we want to compare how long it takes for each of these circuits to reach 50% of the steady state current. Doesn't matter what each steady state current is, we're just looking at how long it takes for each to reach 50% of its final value. So notice we have an inductor and a resistor in series, then we have an inductor and 2 resistors in series, then we have an inductor and 2 resistors in parallel. So anytime we're looking at like relative time it takes for the current to reach a certain value, that's proportional to the time constant. So we're really just ranking the value of tau here for each of these inductor resistor circuits. So we can start by writing that this sort of time that we're interested in is going to be proportional to the time constant, and that time constant is equal to L over R for one of these circuits. And it's important we use the total R for this, the equivalent resistance. So we'll just go through and give a sort of representative time constant to each of these. So first, in circuit A, well, this is kind of our base case because it's just an inductor and a resistor. So tau for this circuit would be L over R. Since everything's identical, I'm just calling each one of the inductors having an inductance L and each resistor having a resistance R. Circuit B, we have 2 resistors in series. And if we're adding resistors in series, we are just adding their resistances. So this would be L over 2R. And then in circuit C, we're adding 2 resistors in parallel. So we could use the parallel resistance formula if we forgot this result, but if you're adding identical resistors in parallel, you just divide the original resistance by the number of branches. So there's 2 resistors R in parallel, so we'd have to divide by R over 2. And again, you could just do 1 over 1 plus 1 over 1 all to the minus 1 to get your REQ that way. So this means that the time constant for A is L over R. The time constant for B is 1/2 L over R. And the time constant for C is L divided by a half, so 2 times L over R. So we see that ranking these in order, we have a 1, we have a 1/2, and a 2. So our ordering would be circuit B has the lowest time constant of 1/2 L over R. Then A has 1 L over R. And then C has 2 times L over R. So BAC would be our ordering, because we're just ranking the time constants. All right. Now we'll talk about constructing an inductor. So a 0.15 meter long coil of wire in total length has 50 turns and a total resistance of 8 ohms. It's wrapped around an iron core, which is 5,500 times more permeable than a vacuum for magnetic fields. Make a solenoid out of this. Each of the coil is a circle with known radius 0.1 or 0.01 meters. So first we'll draw this setup. So again, this setup, it's just a classic way to make an inductor is to take some sort of a magnetic responsive material and just wrap a bunch of wires around it. So for this setup, I'm just going to do my best to just draw my iron core. So a nice beautiful cylinder by me here. And then we're going to wrap some coils around it. I'm just going to draw them really spaced out so we can see that there's some coils on this. But again, you can imagine that if you're actually trying to make this inductor in the lab, you can make a really good inductor by making these coils really tightly wound. And then these ends would be attached to some voltage source. And then just to give us some values here, we said that this length right here is 0.15 meters. We'll call that little L. And then we're also given some other values like 50 turns. So notice this is capital N, which is just the number, not little n, which is turns per meter. We're also given that the mu of this material is 5,500 times bigger than mu naught. Remembering that mu naught is 4 pi times 10 to the minus 7. And that would be Tesla meters per amp. And then the area of each of the coils that we'll need, it's a circle, so it's just pi r squared. So there's some values we'll need for calculating later. All right, so explain why this device will function as an inductor. Well, we said that a series of coils is the quintessential example of an inductor, and that's just because solenoids are great at confining magnetic fields. So you can get very large magnetic flux values through this coil, and therefore it will resist a flux change via Lenz's law. So this object will resist current changes due to Lenz's law. So there's a strong magnetic field in each of the coils. As a result, it's going to oppose changes in magnetic flux by Lenz's law, which is what we said an inductor does. It's just utilizing Lenz's law. So now we'll calculate the inductance of a solenoid. We derived this formula a while ago, but it's actually something we're just given on the formula chart, so we're not going to reinvent the wheel. But to do this, we figured out like the total flux to the solenoid, and then we divided that per unit current and found that the inductance of a solenoid is given by mu of the material used for the core times the number of turns squared times the area of each coil divided by the length. And I'll save us the details of plugging this in, but again, we do know everything. So 5,500 times mu naught, 50 squared, pi r squared of the coils, divided by the length, and we get 0.036 Henry, which would be 36 millihenry. Then assume we attach the solenoid to the battery, and we're going to calculate its time constant. So its time constant, we know the resistance, so it's given to us that the time constant in one of these inductive circuits is L divided by R. And we were given the resistance was 8 ohms. So we're just going to divide our 0.036 henries by 8 ohms and get 0.0045 seconds. And notice this isn't going to be like the RC circuits where we could get very large time constants. This fact that R is on the denominator actually makes it really hard to measure a lot of things in real time with these circuits. So it's very rare that we get inductive time constants that are on the order of something we can measure just on the order of normal seconds. So we typically need special equipment to catch these transient circuits in action. So going on to some quantitative analysis, we said that all of these R over L graphs will look the same as the RC circuit graphs, where they take two forms. If something is increasing to a max value, it takes this form, which the charging function probably isn't the best name for it. I'm looking for a better name for these two parent graphs. But at the time, I call this one the charging function, where we have some curve that starts at 0 and it approaches some maximum value. So we have the max value times the quantity 1 minus e to the negative t divided by tau. And then I call its counterpart the discharging function, where we start at a maximum value and decay to 0. And all of these graphs will look like this. So one of these two graphs will apply to all of the RC circuit quantities we'd want to graph, or all of the R over L circuit quantities we'd want to graph. Sorry, L over R. So if we know if it's increasing or decreasing over time for that quantity, we know exactly which one of these two parent functions it'll fall into. So we have the increasing and decreasing graphs. Of course, we don't need to take this for granted. We will solve the differential equation and show that we get this, but you can save yourself some time just by knowing these parent functions. So for our loop equation, technically Kirchhoff's voltage rule doesn't apply if there's a magnetic flux change, but due to how magnetic flux is defined, we actually get the induced EMF to be equal to the voltage drop across an inductor. So it's totally fine to just interpret what we're doing as the loop rule. I didn't really think it was worth our time to go over this sort of fact that the loop rule kind of breaks when magnetic flux is introduced due to the non-conservative electric fields. That's a whole rabbit hole you could go down, but we will just say that if we want our potential drop, we're just going to use the traditional inductor potential drop formula and just treat it like a resistor in that sense. So we're just going to come up with our loop equation first here. So we're saying that we originally have a circuit that's has no current, but as soon as we flip the switch, we want to look at what's happening in this circuit. So we already said that the inductor should behave like a gap at short times and a short circuit at long times, but we're going to figure out the in-between, and hopefully it follows that parent function that we're predicting it does. So really there's only one sensical loop that makes sense for us to traverse in this case, and we're just going to follow that loop. So again, Kirchhoff's voltage rule, this is a fundamental principle. So whenever we have derived questions, we typically do have to start from the loop rule. So we can start by saying that the sum of the voltage gains and drops has to be 0. So the first thing I do in my loop is I gain the battery EMF. So this is my gain of potential. And then I drop voltage in two places. First, I drop across the resistor. Then I drop across the inductor. Then we'll substitute in expressions for all of these things. So the battery EMF minus, well, delta V across an inductor resistor is IR, just by Ohm's law. And then we'll subtract also the voltage that's dropped across the inductor, which we're just defining as L di dt. And before we box around this, we want to make sure it is a differential equation and not just any equation. And it is. So with capacitors, we did have to substitute to actually get a derivative in here. But notice we have I and the derivative of I in the same equation. So this is a differential equation. You can feel free to move things around, and that would also be valid. So now, of course, we're going to solve this. So consider the following differential equation that models the current through the inductor as it's storing energy, which is the one we got on the previous page. Derive an expression for I of t. So we're not assuming we know anything about what the answer will look like yet, and hopefully we get the advertised parent function. So we're going to start from here, just our original differential equation. Then I'm going to divide everything by r and make some substitutions. So dividing every term by r. And now I'm going to make some substitutions in here just to make the equation a bit easier to look at. So first thing I'm going to do is notice that this quantity, EMF divided by resistance, this left term right here, that's definitely a current. And for reasons we'll see later, I'm going to define this as I max. Minus I minus, and then I'm also going to define this L divided by R quantity as this variable tau. And this is just done to clean up some of the letters so that it makes the equation a bit easier to look at. So now we'll separate. So I'm going to move everything that's not, I'm going to try to move everything to the other side here. So in doing that, let's see, what way would I like to do this here? So we can actually solve for di, so I could get tau times di dt is equal to I max minus I. And then I'll separate and integrate here. So I would get di divided by I max minus I would be equal to 1 over tau times dt. So again, I just separated. So I divided both sides by every term on the right side, and then I moved my tau and dt over to the left. And then we can integrate both sides. So I'll integrate both sides where my current starts at 0 and it ends at some value I. And then my time starts at 0 and ends at some value t. So now just doing the antiderivative of each side. On the left, we would get negative ln of the quantity I max minus I, evaluated from 0 to I, is going to equal 1 over tau times just, well, integrating 0 to t of 1 just gives t. All right, now plugging in our limits on the left side and moving the negative around, we would get ln of I max minus I minus ln of I max is equal to negative t over tau. Because I'm just plugging in I as the upper limit and 0 as the lower limit. Now I'll combine these logs into a single fraction using the subtraction rule. Eliminate the log by exponentiating both sides. And then simplifying. I could simplify this as 1 minus I over I max is equal to e to the minus t over tau. So therefore, I could subtract the exponential from both sides, add the I over I max, multiply by I max, and I get I is equal to I max times 1 minus e to the minus t over tau. And it's important that these aren't actually all the variables we started with, but it definitely helps writing it in this form. So just remember that some substitutions we made is that this I max was the battery EMF divided by the equivalent resistance, and the time constant was equal to L divided by R. So again, do I think that this is a skill that we should allegedly have? Yes. Would I ever recommend doing this whole process? No. I would just show that you integrated. I would just show the separation and integration, and then I'd skip right to the answer. Because it will not change. This will always be what that answer looks like if the quantity is increasing over time. If it's decreasing over time, it's just the decay term, meaning you don't have that 1 minus. It's just I times e to the minus t over tau. But now we'll graph I of t. So again, we already know what this parent function looks like. It just looks like something where the current is initially 0, and then it approaches some steady state value. And it does want us to label any sort of asymptotes / intercepts here. So there's my horizontal asymptote, and we said that this represents the maximum current in the circuit, which is the battery EMF divided by the resistance. Okay, now we have a classic sort of 2-switch setup where we can flip it between an inductor storing energy and inductor releasing energy. So first, we're going to flip the switch to position 1 when the inductor has no stored energy, and allow it to not really charge up, but the current will go through the inductor, meaning it'll be storing energy in its magnetic field. So first we're going to flip it to this position, So we get just the left side of the circuit as our loop. So writing a differential equation here, notice that it is just going to work out to what it was before, where we gain some EMF across the battery, then we drop some voltage across the resistor via Ohm's law, IR, then we drop some voltage across the inductor via the induced EMF relationship with the inductor. And if you add up all the voltage gains and voltage drops around a closed Kirchhoff loop, you must get zero because of energy conservation. So now, on the same set of axes, graph qualitatively what's happening to the potential difference across the resistor R and inductor L over time in this first position. So again, whenever graphing things in physics, we kind of want to look at our extreme cases. So maybe let's just look at the inductor first. So we know that delta V across the inductor, well, originally, the inductor is very displeased that the current is changing through it when we flip the switch. So it's going to act like a gap in the wire, holding all of the battery EMF. But then over time, the inductor is going to reduce the rate of current change and eventually be happy in its steady state and then have zero EMF across it. So we know that delta V across the inductor is going to start with the battery EMF and it's going to end approaching zero. Then for the resistor, either by understanding what's going on with the current or knowing that Kirchhoff's loop rule has to work, it's the opposite. Because if there's no current in your circuit, we have no voltage drop across the resistor. And then if there's lots of current in the circuit, that must mean that we have maximum voltage drop. Or just realize by Kirchhoff's loop rule, if the full EMF is dropped across the inductor, there must be zero EMF dropped across the resistor, and vice versa. So we know the resistor is the opposite. Now we just got to figure out some connectors. So first, for the inductor, well, it's decreasing over time, and we said in any of these circuits, decrease over time always follows this exponential decay relationship. And then increase over time always follows this sort of asymptote relationship where it increases approaching that horizontal asymptote. So if we're to actually write functions for each of these, the inductor voltage would be the battery EMF times quantity 1 minus e to the t over tau, whereas the resistor would have the 1 minus situation, whereas the inductor would just have the battery EMF times e to the minus t over tau. So now for our long-term analysis of this circuit, drive an expression a long time after the switch is closed. First, the current through the inductor. Well, we know that the current is just going to be equal to the battery EMF divided by Req after a long time. And we know that because if I just draw my circuit, we said that at long times, the inductor does not mind because it's a steady state current, so the inductor acts as a short circuit. And there actually really isn't an Req in this situation because it's just a single resistor, so it's just the battery EMF divided by R. Then for our potential energy stored in the inductor, our formula for that is that U is equal to 1/2 Li squared. It's like our kinetic energy. So it's 1/2 times L times the current squared, which is epsilon over R. So this would be our expression. So then after a long time, meaning we've reached this steady state current, we switch the circuit over to position 2, and it closes for a long time. So let's see what that circuit looks like. So we definitely have a lot of current in the inductor at this time. It's that steady state current. But then we just quickly flip the switch over, and we get this loop where it's everything on the right side. So for our REQ, in this case, we have no battery, sorry. We have our inductor, and then that is going to discharge through a parallel combination of 3R and 6R resistors. Yep, I did get the order correct. So this just says derive an expression for the equivalent resistance. So there's a chance you actually just can look at this and know, because it's actually a special pair, 3 and 6. 3 and 6 add to something nice in parallel. But, of course, I always recommend just doing it. So, reciprocate each of the resistances. So we got 1/3 plus 1/6, all the minus 1 times R. And magically that works out actually to 2. So, again, when we ask what is 3 plus 6, there's that new math that all the parents are scared of, because 3 plus 6 is actually 2. We're just, if you're adding parallel resistors at least. So now we'll write ourselves a loop differential equation that we could use to solve for the current as a function of the time elapsed after it's moved to position 2. So to make your life easier, do not even attempt to write a loop equation unless if all of your resistors have been compacted into one. So I am just writing my circuit as the equivalent 2R resistor here. So in this case, we know that the delta V across the inductor has to be the same as the delta V across the 2R resistor. So then we can just apply Ohm's law to this situation and get negative L di dt as our inductor voltage is equal to I times 2R. And in terms of sign, notice that the signs don't match, that our di dt is going to be proportional to negative R over L times I, indicating that decaying exponential that we expect. All right, now on to actually solving this. So derive an expression for the current through the circuit as a function of time when the current is in position 2. So we just said the negative L times di dt is going to be equal to 2R times I. So this one's actually way easier to solve analytically, but it's almost easier to actually just see the answer to it. So if we get everything solved for di dt, we could write di dt is equal to negative 2R divided by L times I. So we're just asking what function is equal to this constant, negative 2R over L, times itself. And we know that that's actually just an exponential relationship with some constant that's just defined as the initial value. So if I were to just skip to the answer, I can actually just look at this and I know that the answer should be I is equal to the maximum current, which is the battery EMF divided by R, because that's the current our circuit started with, times E to that proportionality constant, negative 2R over L times I, or sorry, times T. But just to kind of match, to show like what the tau would be equal to, I'll just write this kind of in its more common form that we'd actually write it in, even though it looks stranger. So I'd write this as e to the negative t divided by L over 2r. Just so we could see that sort of L over r time constant up there, I just wrote the entire constant in the denominator. That's totally equivalent, but this is just showing that time constant. So, of course, we can quickly just show that like this is the actual answer. So, if we separated the differential equation, we get di over I is equal to negative 2r over L times dt. And then we can integrate both sides. So our current changes from its initial value of epsilon over r to its final value of I. And then the dt, well, we're just integrating from 0 to t. So we'd get ln of I divided by epsilon over r is equal to negative 2r over L times t. And we can see by exponentiating both sides of this, we do in fact get the original relationship that we think we'd get, where I would be equal to epsilon over r times e to the minus 2r over L times t. But again, what I'd recommend doing in practice is just kind of setting up the differential equation, and whenever you feel like you personally know kind of what it will look like, skip to that answer. I do recommend showing at least integrating though. This one, not bad at all. Like this one was not bad to integrate, but if we go back to this, I never want to do that in an exam setting, especially because I know the answer. There's some problems I don't want to do, but I have to do them anyway. Just because I don't know the answer. But again, we know what the answer to these RL circuits, these L of R circuits will be before we even do the problem. It's either going to be that e to the minus t over tau or the 1 minus e to the t over tau. All right, now we'll graph this. So sketch a graph of the current through the inductor as a function of time. So first, we had the switch in that first position where there was initially no current, and then it reached its max value, and then we flipped the switch, and the inductor released its energy. So first, we always deal with our, like, what are some known values? So we do know that the value of the current in the inductor peaks at this battery EMF divided by R quantity. So we know that it's reached that steady state current as the switch is changed. We also know there's initially no current through the inductor, and at long times there shouldn't be. So first, for this connector, we know that since it's an L over R circuit, it's going to be an exponential. And just to show, I don't know why that's green, and just to show the exponential nature here and the fact that it's been a long time, I'm going to show the fact that this current is going to peak and kind of stay at that value for a while. Then we know that long times after the switch is closed, the inductor has sort of used up all its energy, so there's no current. And now we'll think about how to draw that. We know it's a decaying exponential. And just to pay really close attention to detail, our first time constant was L over R. But our second time constant was L over 2R. So actually, it should take less time for the relative discharge to happen versus the charge, if we were to look at those sorts of graphs. So I'm actually going to make a very rapid exponential decay. So that would be kind of what our graph would look like. All right, now for some lab-related questions. So first, A group of students wish to calculate inductance of a homemade solenoid. They have a solenoid whose value we wish to calculate. We're assuming it has negligible internal resistance. They have a 12-volt battery, a 5-ohm resistor, a switch, and a very high sampling rate voltage probe, which is definitely necessary for this lab. So first we'll draw a circuit. And again, to effectively do a best fit, we want to only graph an exponential decrease, because that just makes the linearizing, well, possible in this case. You could use the different graph, but then you'd have to curve fit. So first we'll draw an L over R circuit. So we have a battery. Then we have an inductor. Then we have a resistor. And we have a switch. So what we need is a circuit that the students could construct to measure the voltage across an element that decreases over time. So we have to think, where could I place a voltmeter such that the voltage would decrease over time? Well, we know in this circuit that if I flip the switch, the inductor is initially very unhappy and is going to completely cut off the rest of the circuit, so there's no current, meaning all the voltage drop is across the inductor. Similarly, at long times, the inductor is happy, so there's no voltage drop across the inductor. So this would be where we have to wire our voltmeter. So I'm wiring my voltmeter in parallel, because again, voltage doesn't go through something, voltage is across. So we're probing the voltage at two ends of the inductor. If we did the resistor, we'd get that exponential rising graph. So again, we're expecting that if we do this, graph of delta V across the inductor as a function of time, we would get something like this, that exponential decay. The resistor would give the opposite behavior, where it starts at 0 and peaks at the battery EMF. So now we can describe how to actually collect the data to calculate the unknown inductance L. So again, you're going to use this sort of voltage probe. You're going to start timing when the switch is closed and figure out when this decay starts. And as soon as the decay starts, that's sort of your beginning of the data. And then as soon as it's sufficiently close to 0 at some set time, you could stop the data, and then you have a list. So you're just trying to generate this graph up here. So start collecting voltage data. Once the switch is closed, create a voltage versus time data table. Then we're going to talk about how to analyze this data to calculate L. So because we are smart humans and just remember what these functions look like, we don't need to do the differential equation here. We know for sure that since it's a decay, that delta V across the inductor is going to behave using the discharge parent graph. So we know that this is the graph that we're generating. So this is the model that we're fitting to. And just like with capacitors and RC circuits, the thing that makes this linearizable is to take the natural log of both sides. So I'm just going to take the natural log of both sides. And then we'll just do some log properties here. So we're actually done messing with this side of the equation. So that's sort of our y variable, is natural log of delta V across the inductor. And then by splitting and using logarithm rules, we'd get -1 over tau times t plus the natural log of delta V max. because a product of logs can be split via addition. So what this gives us now is a y equals mx plus b relationship. So we would graph ln of delta v across the inductor as a function of time. Of course, there's alternate solutions. Some of you are what I call slope purists and just like to have the quantity of interest sort of solved for already. So just kind of labeling some values here. This would be our y. This would be our x. So this means our slope, m, is negative 1 over tau. And our natural log of v max is a very ugly looking y-intercept. So we know that the slope of this graph would be equal to negative 1 over tau. But tau in an L over R circuit is L over R. So this means if we're solving for our inductance L, we could just get that inductance L by taking the negative of the slope. And after taking the negative of the slope, we'd have that sort of resistance on top. Because if slope is negative R over L, then that means that L is negative R over the slope. So let's just re-look at that procedure. So first, get a voltage probe, generate this graph, meaning get voltage and time data. Then, graph natural log of voltage as a function of time, because the slope will be related to the time constant, which is related to R and L. All right, suppose we have an ammeter, but not a voltmeter. Can we do this procedure? Well, let's think about it. So if I had an ammeter and put it in this circuit, well, inductors block the current initially. So I'm not getting less current over time, I'm getting more current over time, so I get that sort of increase function that I don't like to analyze. So actually, no. I'd have to have a voltmeter to do this procedure because the current doesn't decay over time. So we can't use that exponential decay model. Then to conclude, we'll just do an example that's just like this, just with some actual numbers. So once again, we have a situation where an inductor, 30 millihenries, is releasing its energy at t equals 0 through a resistor of unknown R. And we record current as a function of time using a high precision current probe or an oscilloscope or anything like that. So first, indicate a set of quantities that can be graphed to yield a linear relationship for the data. So we know that because this is a decaying situation, where we have a lot of current and less current, and it's a simple circuit, we know that it follows our typical form, except it's just current this time instead of voltage. So the current through the inductor is going to be equal to the initial current times e to the minus t divided by tau. So as such, we actually can apply the exact same model we worked at in the previous problem to do this, just replacing current, just replacing the voltage with current here. So again, if I were to write that in y equals mx plus b form, I would get the natural log of the current is equal to negative 1 over tau times t plus the natural log of I0. So this means that we could graph ln I on the y-axis and t on the x, and we'll get a straight line. So just to spare us from watching me graph by hand, we'll of course transition over to Desmos for this next part, where we'll actually graph the data and do all the analysis in there. So we'll come up with our regression using Desmos. So we'll do that real quick. All right. So here is our data in Desmos. So here's some general physics tips for us in Desmos is I always rename my x and y to the actual letters that's being graphed. So first I have my raw data of current versus time. And this data could actually potentially pass for being linear if you didn't look enough, but it actually is exponential decay. But what we'll do now is we'll linearize. So this is how I suggest linearizing. So first we'll cover up kind of the raw data because we're not going to use that. But I'm going to make two new columns. So I like to do everything just in its own linearized box. So we did not adjust anything on the x-axis. We used time again. So I'm going to call that T1 again, but just so it shows up, I'm going to put a 1 in front, just so I get to see the nice numbers. And then instead of graphing current on the y-axis, we graph the natural log of current. So notice I now have a graph of ln of the current versus time. And if I zoom fit that and look what that graph looks like, well, that's quite linear. And again, there is a y-intercept, but we expect that. So then we can just hit auto regression on this little side button here. And this tells us, first of all, notice that r squared is equal to 1. That's because I made this number, so it worked. But we get the following equation where y is equal to negative 333, basically, x plus 0.91. All right, so that was a success with Desmos. So using that graph, we said that y was equal to about negative 333 as our slope times x. So negative 333x plus roughly 0.91 as our y-intercept. So now that we found our regression, and it's always good practice if you come up with some equation to actually like say where you got it from. So I say I'm just write linreg out of habit using the TI calculators, but we just want to show that these regression equations don't just pop up from nowhere, so we use technology to get that. But then based on our model, we said that the slope was equal to 1 over the time constant. So we said that the slope was equal to negative 1 over tau, which means that the time constant of the circuit is just going to be equal to negative 1 over the slope. And let's see, what would this be? Well, 1 divided by 333, about 0.003 seconds. So that's our time constant. We didn't really want that, but it's going to help us get what we wanted. So we also know that this tau is equal to L divided by R, and we actually know L in this problem. So R is just going to be L divided by tau. And then we can just plug in, because we were given that the inductance was 30 millihenries, so that's 30 times 10 to the minus 3. And then our time constant was 0.003. And dividing that out, we get 30 times 10 to the minus 3 divided by 3 times 10 to the minus 3. So that looks to be basically 10. So our resistance seems pretty close to 10 ohms. Then we can also find the initial current through the circuit, because that's related to the y-intercept. So we said that the y-intercept was the natural log of I0, just based on our model, because we see that's the tacked on b plus b term, ln I0. So therefore, our y-intercept of 0.91 is equal to the natural log of I0. So to undo that log, we just e both sides, for lack of a better term. So I0 would just be e to the 0.91. And this is approximately 2.5 volts. Nope, definitely not volts. Sorry, amps. And then we can calculate the initial voltage across the resistor because we know I and R now. We solve for R, we solve for I. So delta V, unsurprisingly, is IR. So we can just multiply our 2.5 amps of current by our 10 ohms of resistance and get 25 volts of potential difference across the resistor when the switch is first closed. All right, that's everything about the transient state.